So in this video, I want to give a more quantitative or rigorous derivation of the quantum mechanical tunneling, or the barrier, the potential barrier. But there actually turns out to be a very good derivation of it in the book Introductory Quantum Mechanics by Richard Lieboff, which I've written over here. This book was published in 1980, and it's a very good undergraduate text in quantum mechanics, and it's a good reference. So instead of me just repeating his derivation, what I wanted to do was to actually just go through. So I've copied out that section of the book, his book starting at page 217, and I just wanted to go through this section of section 7.7 in Lieboff's book, where he talks about the rectangular barrier, the potential barrier, and in particular we'll get to the case of tunneling. So he sets up the regions of interest. So the width of the barrier goes from minus A to A, and that barrier has a potential of V, whereas to the left in region 1, to the left of the barrier, the potential is 0. In region 3, the potential is also 0. So on the next page he has a schematic of it, where we've gone through some of these problems in class. So you can see that in region 1, you have these propagating waves that have an incident wave, this one A e to the I kx, and a reflected wave B e to the minus I kx. And then to the right of the barrier, you have a wave which is a normalization constant F, and then it's traveling to the right, so it's e to the I kx. And then at the barrier, so in this case the energy E is above the level of the barrier, and so above the barrier we have traveling waves, one going left and one going right. So if we list it down here, if we list the wave functions in each of those regions, you have the wave function in region 1 with the incident wave with a normalization constant A, and the reflected wave with a normalization constant B, and then the Ki wave number you can get from this equation for the energy. In region 3, you also have a traveling wave, and we only consider the one that's transmitted through, not a traveling wave going into the barrier to the left, but it has the same wave number, Ki. And then in region 2, you have, again, traveling waves because the energy is greater than the potential barrier, and so you have a traveling, but now the wave number is K2, which you can calculate from the difference of the total energy and the size of the potential barrier. So what he does is to say that, again, we're interested now not necessarily in solving for the wave functions, but getting the transmission and reflection probability coefficients. And so in this case, the reflection coefficient would just be the ratio of normalization constant B to A squared, and the transmission would be the normalization constant F divided by A. So in this case, it would be the normalization constant for that transmitted wave in region 3. So the question is, how are we going to get these normalization constants? And the idea is to solve the boundary conditions. So we basically have 4 equations for the boundary conditions. The first equation right here is the boundary condition where the wave function in region 1 is equal to the wave function in region 2, and then evaluated at the boundary where x is equal to minus a. The second equation is the boundary condition where the first derivative with respect to x are equal. So the wave function and the change in the wave function have to be continuous. And so you have on the left-hand side the derivative of the wave functions in region 1, and on the right-hand side, the derivative of the wave functions in region 2. And in both cases, the normalization constant A has been divided out, so we're now getting the ratios of the normalization constant B to A and C to A and D to A. So the third equation is when the wave functions are continuous at the second edge, where x is equal to A. And the fourth equation is where the derivatives, the change in the wave functions, are continuous at the barrier where x is equal to A. So we don't need to know the ratio of C to A or D to A. So instead, we just want to use equations 3 and 4, solve for C divided by A and D divided by A in terms of the ratio F divided by A. And when we do that, then you can substitute them in to equations 1 and 2. So now you'll get an equation where the ratio of F divided by A and B divided by A are then going to be equated. And so finally, so basically there are 4 unknowns. These ratios of B, C, D, all with respect to A. So 4 unknowns, 4 equations. We can solve that. And when you do, after a lot of manipulation, which of course I'm leaving out because I just want to follow along in Leboff's text, you get an equation for F divided by A, which works out to be basically sines and cosines. So doing all of that algebraic manipulation, you reduce those exponential, the e to the I, k, to cosines and sines. So actually, if you notice, if we kind of take this apart, the first term has the k1 dependence to the exponential, and in the bracket, the cosine and the sine have the k2 dependence. So the dependence of the energy above the barrier is inside the bracket, and this is to the power of -1. So here are the 4 equations. So I suggest to the students that they take these 4 equations and solve for f of a to prove to yourself that you can actually achieve this result. Now, once you get f divided by a, you can go back and look at the relationship between b divided by a and f divided by a, and what you find is you get this relationship where this is 2 times, but you can divide both sides by 2 to get the ratio, and what you have is this result right here. Again, it's in the best interest of the student to spend some time and work through those equations to trust that you get that result. Okay, so now that once we have that, the f divided by a squared is the transmission probability. B divided by a squared is the reflection probability. Those 2 quantities added together should give you a probability of 1. And so even though these ratios of normalization constants are complex, so f of a has an I term times the sine, b divided by a has an imaginary number I in there as well, squaring b divided by a is really taking the complex conjugate and multiplying it by that number. Very similar to what we did in class. So now you have an energy dependent, so the k's, k1 and k2, so you have an energy dependence to the transmission and reflection probabilities. Not only that, but you also have an A dependence. So you have half the width of the barrier is also related. So the larger the barrier, then the lower the probability that you're going to get transmission across the barrier. And then K2 has the actual potential level itself, V, and so then that is going to also impact the transmission probability. So, if you make the potential barrier very tall, then that's going to impact, probably, there's going to reduce the transmission probability and increase the reflection probability, whereas if you made it very wide, that would also probably increase the reflection probability and decrease the transmission probability. So in the end, what you can find is we can rewrite this now. We can rewrite now we can write as 1 over the transmission probability. So A divided by F squared, which then gets that big bracketed term out of the denominator. But so it's a little bit hard to interpret what is 1 over the probability of transmission. But the equations are a little easier to calculate, and what you find is you get something that looks like this, once you've squared that ratio of normalizations, which then you can rewrite, and he's already boxed it off here, as one. Now he's changed the k's, these wave numbers, into energies, and you get something which is, again, more manageable to understand. The fact that 1 over the probability is equal to 1 plus this term, where the sine squared now is going to be a ratio less than 1. So that's going to reduce that in the equation. But now you have something that's it's clearly energy dependent. You can see the relationship to the potential V, the relationship to the total energy E, and the difference between it. So it has all the pieces in it to solve the problem of how to get the transmission probability, and it's related to the width of the barrier A, the potential height V, and the total energy with which you start off E. So all those pieces you can use to calculate what the transmission probability is going to be. In the next video, we'll actually lower the energy E less than V and see where the tunneling comes about.